Hello dear learners, in this video lecture we will discuss about finding the Hamiltonian cycles in a graph using backtracking. So first of all, let us discuss about what is a Hamiltonian path. In an undirected graph, it is a path that visits each vertex exactly once. Okay, so there is a path in undirected graph. Okay, so remember that the graph which is given to us is undirected, and here if there is a path which visits each vertex exactly once, then that is called a Hamiltonian path, right? For example, in this path we are visiting different vertices. All vertices are distinct. v1 is not equal to v2 is not equal to v3, and this is a path, right? And such kind of a path where v1 is not equal to v3 is not equal to vi, that is called Hamiltonian path. Now, Hamiltonian cycle. Hamiltonian cycle is also known as Hamiltonian circuit. Now, what is a Hamiltonian cycle? It is a path such that there is an edge from the last vertex to the first vertex. So in the previous example, the path was like this. v1 was connected to v2 is connected to v3. So if there is an edge from v3 back to v1, then this becomes a cycle. And in this cycle, all the vertices are distinct. So this is known as Hamiltonian cycle. Okay. So our problem is to determine whether the given graph contains a Hamiltonian cycle or not. Okay, so if the graph does not contain any Hamiltonian cycle, then the algorithm will return a false, but otherwise it will print the path. Okay, so what are the inputs and outputs to the algorithm? The input is the adjacency matrix V cross V, where V is the number of vertices, right? And the output is an array path, and the size of that array is equal to V, that is equal to the number of vertices in the graph. So this path array will represent the Hamiltonian path. So path I, that is any entry in your this path array, it will represent the ith vertex in the Hamiltonian path. Okay, so it also returns a false if the graph does not contain any Hamiltonian path, right? So let us take the example here. Here we are given a graph with 5 vertices, right? And if we try to analyze this graph, then we will find that this graph contains a Hamiltonian path, right? So if we go from A to B, then B to C, then C to E, so this is a Hamiltonian path, right? And again we go from E to D, still this is a Hamiltonian path because all the vertices are distinct. And from D, if we connect to A again, now this becomes a Hamiltonian cycle, right? So this is the Hamiltonian path, A, B, C, D, sorry, not D, E and then D, right? And if we remove this vertex, okay, sorry, not vertex, this is an edge. If we disconnect D and E through this edge does not exist. Okay, then if we try to find any Hamiltonian path, then I think now this graph does not contain any Hamiltonian path, right? For example, if we are not a Hamiltonian path, actually Hamiltonian cycle. Okay, so if we try to go from A to B, it's okay. Then B to C we can go, from C to E we can go, but from E we have to go to B again. Okay, so and from B we can go to D, and from D we can go to A. Okay, now if you see, the Hamiltonian cycle is containing the vertices A to B, then B to C is the edge, then C to E is the edge, and from E we are again going to B again, right? So it means we are repeating this vertex B, right? And from B we are going to D, and from D we are going back to A. So this is a cycle, but this is not a Hamiltonian cycle because the B vertex is repeating in this cycle, right? Okay, so what is the backtracking approach? We start with the vertex 0. Okay, so we create an empty path array. So initially the path array which is containing v vertices is empty, and initially we add vertex 0 to it because we start at vertex 0. Suppose we start at vertex 0, although we can start at any vertex. Okay, and then we add other vertices one by one starting from the next vertex after 0. So after vertex 0 we have vertex 1, we vertex 2, we have vertex 3, and so on. Okay, so we one by one keep on adding those vertices, but we have to satisfy the constraint of this problem of Hamiltonian cycles. The constraint is that there should not be any vertex which is repeating. Okay, so no vertex should be repeating. So before adding a vertex we have to check whether it is adjacent to previously added vertex and not already added. So we can add a vertex only when this is adjacent to the previously added vertex. So if we add vertex 0, from vertex 0 we can add only those vertices. Suppose this is vertex 0, it is adjacent to vertex 1, this is adjacent to vertex 2, but this is not adjacent to vertex 3. Okay, so from 0, this is the previously added vertex. From 0 we can add a 1, we can add a 2, but we cannot add a 3, right? Because there is no path from 0 to 3. So we can add only those vertices which are adjacent to 0. This is the one condition, right? Because there must be a path. And the second condition is the vertex should not be already added. If the vertex is already added, it means you are repeating the path. Okay, but the constraint in Hamiltonian cycles is that no vertex is repeating. Okay, so if we are able to find such a vertex, then we will add that vertex as the part of the solution like this. But if we do not find a vertex, then we will backtrack. Okay, and after complete search of the state space, if we do not find any Hamiltonian path which is satisfying the constraint that no vertices should be repeating, then the algorithm will return a false. Okay,
so let us look at an example to understand this backtracking algorithm to find the Hamiltonian cycles. So let us use the same example which we saw in one of the previous slides. So there were 5 vertices A, B, C, D and E, and the edges were like this. Okay, so now we are ready to execute the backtracking algorithm on this graph. So let us start with vertex A. Although we can start with any other vertex, but the condition is that in any Hamiltonian cycle, your path, no vertex should be repeating in your path, in your cycle. Okay, so we have A here. Okay, and let me also draw this path array. This path array, it will contain there are 1, 2, 3, 4, 5 vertices, so it will contain 5 entries. Right. So the first one is A. We have considered A. So we have added A as a part of the solution. From A, where can we go? We can go to B. We can go to D. Right. So there are 2 edges which are connected with A. And we will try these options in lexicographic order. So first let us try option B. There is a path from A to B, right? Because we picked it from this adjacency list of A, right? And the second thing which should be satisfied is that the vertex which you are considering should not be already in the solution. So B is not already in the solution. So we can add this as a part of the solution. Now we have added B. From B, where can we go? We can go to A, to C, to D, and to E. This is the adjacency list of B, right? So there are 4 edges. So let us first try A. So when we try A, we see that A is already there in the solution, right? So it means this is not a feasible solution. We have to backtrack. The second option is C, and C is not already in the solution, so we can add C. Okay, and from C, where can we go? From C we can go to B again and to E, right? There are 2 options, 2 paths. Let us try the first one. The first one is trying B. So if we try B, we can see here in the solution B is already existing. So it means this cannot be the part of the solution. We have to backtrack. And the second option which we can try is E. E is a valid option, right? Because we are not repeating E. E is not already there in the solution. Okay. So we have added E in the solution. Now from E, where can we go? From E we can go to B, C and D, right? There are 1, 2, 3 options. So when we try the first option, B, this is not possible because B is already there in the solution. The second option is C. C is also not possible because it is already there in the solution. And the last option is D. D is feasible, right? Because D is not already there in your solution. Okay. So now from D, you can see here we have filled this path array, right? So it means you have explored all the paths. Okay. So you have explored a complete path, right? A to B, then B to C, C to E, E to D. Now this path can form a Hamiltonian cycle if from D there is a path to A. Okay. So let us look at the adjacency list of D. D is connected to A, B, E, right? So it means there is a path from D to A, right? So it means this solution is the part of the Hamiltonian cycle, right? A to B, B to C, C to E, E to D, and D contains an edge back to A. So this means this is a solution, right? Okay, so this is one solution, but backtracking does not stop here. It explores all the options which are available. Okay, so when we backtrack from D to node E, here we have explored all options of E. So again we backtrack to node C, and here also we see that we have explored both the options which are available from C. So we backtrack to node B, and from node B we can see that we have explored this option. We can also explore the other option which is available, that is to D, B to D, right? So this can be the part of the solution, right? Okay, so from D we can go to A, but A is already explored. The second option is B. B is already explored. The third option from D is E. Okay, so E can be the part of the solution, right? So we write E here. And from E, where can we go? From E we can go to B, but B is already there. From B, from E the second option is trying C. Yeah, C can be the solution, part of the solution. Okay, so now we have filled this path matrix, right? So this means we are at a leaf node, and this can be the solution if C contains an edge back to A. But when we see here, C does not contain any edge back to A, so it means this is not a solution, right? So from here we backtrack to node E, and at node E we have explored B, C, and we are left with D. Can we write D here? No, we cannot write D here because D is already the part of the solution. Okay, so we backtrack to E, and for E we have explored all the options. We backtrack to D. For D we have explored all the three options, so we backtrack to B. For B we have not yet explored the fourth option, that is E. Okay, so you can see that we are going in a depth first order, right? Because backtracking, all the problems which are solved in backtracking, they are solved in a depth first manner, right? So from B we were going to E, right? From E we can go to B, but not an option. Then we can go to C. Yes, this is an option. Let me write it here. And from C we can go to B, but again this is not an option. We can go to E. Again, this is not an option. Okay, so we have explored all the two options from C, so we backtrack. We go back to E, and from E we have yet to explore the other option which is available to us, that is D. Okay, so when we try this option E to D, then from D we can go to A, but this is not feasible. We can go to B, this is not possible. We can go to E, again this is not possible. A, B, E, all the three options which are available at node D, they are not possible. So we backtrack to E, and when we see E, we have explored all the three options, B, C as well as D. So from here also we backtrack to B, and when we look here, we have explored all the four options which are available at node B, A, C, D and E. So again we backtrack and we explore the yet unexplored node D from A, right? And this will also be solved similarly in the depth first order, and I encourage you to complete this problem for node D. Draw the depth first search tree or the state space tree for node D and check whether there is any other Hamiltonian cycle which is possible in this graph or not. So I leave this as an exercise for you. So this is all about the Hamiltonian cycles, finding the Hamiltonian cycles in a graph using the backtracking approach. Thank you.